All right, so you're looking at this right here. And our first, what we want to do is it says on your sheet, we want to rotate this. First of all, if this is the function, say f, if this is the function f, and say this is 3, is that what it is? 1? Okay, it's 1. Then how would you write a set of functions or equations that would define this region right here? This one that looks like a shark fin, okay? That thing that looks like a shark fin. How would you define a set of equations or functions, a set of mathematical statements that would indicate this right here? So normally you're going to be given a set of mathematical equations or functions, and you have to come up with this picture. So let's do it in reverse first. Here's a picture. This is a function f. That's x equals 1. So what set of equations or functions would indicate that region? Go. See if you can do that. So this is not a question on the page. This is, I made up a question here. No, he's got him. Ben's got him back there. Okay, what's one of the defining characteristics? Yes, sir?
Fx is greater than or equal to 0, less than or equal to 1.
So you don't. So f of x is f of x. So are you talking about? I think you're talking about just y coordinates. So you're saying y coordinates are what?
Less than or equal to 1 and greater than or equal to 0.
No, you're mixing. You got apples and oranges there because 1 is x and 0 is y.
Yeah, but on our graph, 1 is also, anyways, less than or equal to f of x.
Yep. There you go. So as an inequality, this is one way you could do it. You could say y is greater than 0 and less than f of x. And then what else? So would that get all these points exactly? All right, yeah, so then an x has to be, right. Okay, so now a different way you might see this is that, so that's one way we could do it. Or we could say the region enclosed by what? The region enclosed by what? So y equals 0 or x equals 0? Y equals 0 or x equals 0? It would be y equals 0, okay? Or the x-axis. The x-axis is not x equals 0. The x-axis is all points where y is 0, right? Where you don't go up or down. So y equals 0 is the x-axis, okay? The region enclosed by y equals 0 or the x-axis. What else? X equals 1. That's the vertical line. And y equals f of x. So if you were to say the region enclosed by these three things, you would get the shark fin. All right? Y equals 0, that's the bottom of it. X equals 1 is the right side. and f of x is the top. And that will give you that region. Okay, so we want to, this is normally how you'll be given situations. And you have to come up with the region, the curves, the boundary, and the region in question. Okay? So this, we want to rotate this around the y-axis. We want to rotate this around the y-axis. And so I'm going to show you the animation, but normally you won't have an animation for these problems that you get in the homework and the exam. You're just going to have to imagine it and draw it the best you can. So let's practice that. So that's either of the left-hand graphs there is to sketch the empty shell that you'll get, the empty three-dimensional shell that you get if you take our region, or you take our perimeter there, the shark fin perimeter, and rotate it around the y-axis. Can you imagine it, and can you get a sketch good enough so it has some degree of accuracy? It doesn't have to be artistic, but you've got to somehow imagine that empty shell and be able to sketch it so someone else knows what you're talking about. Try that. Where are the rest of the worksheets? Ben has some. Everyone have one? Okay, so yes, I'm going to show you the nice, pretty computerized picture, but you have to know how to sketch them. So here's some suggestions for sketching. The first thing is, draw the mirror image when this thing has rotated through half of its revolution, right? When you've revolved it halfway, draw that mirror image, and I made that dotted like that, okay? And then we take these top corners, and to show it circularly, you draw like an ellipse, right, an oval. So you get the perspective, and your mind tells you it's a circle, right? Looking kind of from above. Your mind tells you it's a circle. Do that same thing with these bottom corners. And that pretty much does it. Okay? So that's just suggestions for sketching. Okay, so now, any questions on that?
Do we need to take care about dotted lines and
No, it's just so you know. Dotted lines I just use for what you can't see, and solid you can. So it's another thing that might help with the drawing. But this is just for use for your own ability to solve the problems. There's no right and wrong here. We just want to make the best image that we can. Okay. So let's take a look at, see if this agrees with it. So we're going to sweep around like this. And what just happened? We just formed an empty shell. So the question is, where's the shell? Is the shell like inside the bowl, or is the shell below the bowl? Is the empty shell that we're going to fill, is it below the bowl or like inside the bowl, above the bowl? You should be thinking it's below, right? Because it was this, if I go halfway and kind of look inside here, turn around. So we're going to be filling in this space that we created by the original thing, right? We're going to be filling that in. So it's below the bowl and above the x-axis. So the first thing you want to do is, in your top one, you want to first sketch delta x intervals of 0.2. I think every tick mark there is 0.1. Is that right? Is every line on the grid point 1?
Yeah.
So you draw delta x intervals of point 2, maybe lightly, not too dark, okay? Sketch delta starting at 0, delta x intervals of 0.2. So will those be vertical strips or horizontal strips? Delta x intervals of 0.2. Will those be vertical strips or horizontal strips? You should be thinking vertical. Vertical strips. Go. Sketch those. Okay, so now, what does it say next? So now we're going to imagine, we're going to use cylinders through delta x intervals to fill up this empty shell. Okay, so we're going to start at x equals 0 and imagine what? X is going to increase through these delta x intervals, and it's going to create shells that fill up this interval. So can you draw the one shell from 0.6? So if the current interval is from 0.6 to 0.8, can you draw the shell that's in process, right? In process. So we've gotten to the interval starting at 0.6, and we want to show a shell that's not yet done, because we want to think of that shell being generated through the current interval. Does that make sense? So starting at the interval at 0.6 to 0.8, we're in that interval, and we want to think about x increasing through that interval and the shell being generated through that interval. So you're going to draw a shell that's like in process in that interval. See if you can do it. It's the shell for the interval from 0.6 to 0.8. One of your delta x intervals should be from 0.6 to 0.8. So as x increases, it gets to 0.6, and it's going to start a new cylinder. So as x increases from 0.6 to 0.8, there's going to be a new cylinder that's going to be created. And you're going to draw that cylinder as it's in process, as it's being generated through that interval. Does that answer it?
Yes.
So the interval is from 0.6 to 0.8. Okay, and so if we're talking about the cylinder that's in process here, then it's got its starting radius there, and we're thinking about x increasing through here. So say this is dx. Dx is going to be like the thickness of our cylinder there, and x is increasing through here, and so we're still in process, so it hasn't finished yet. So maybe it's like that. But we're going to use the height of it to be the starting function value there. And then, what will that cylinder look like that's going to be the one that's the next one here, filling up the shell that we have, right? So, hopefully you drew something like this, because it's going to be a cylinder like this. That's the inside. Does your cylinder look like that? Or something like just good enough. It doesn't have to be perfect, doesn't have to be beautiful, artistic. Some of you will like to make pretty pictures, that's great. But just good enough so that you have the right image of it. And so x is increasing through these intervals, and in each current interval, this shell is growing. What is growing about that shell? And this is going to define what the rate of change is, right? The whole ball of wax here is what's the rate of change what's the rate of change of volume as we fill up this cylinder? So what is changing? Is it the area of the base? Is it the area of the base, i.e. the radius, or is it the height of the shell in the current interval? Which of those two, or both? Which is changing? In the current interval. Does the radius change or the height change or both of this cylinder? You should be thinking just the radius. Just the radius is changing. In the current interval, the height's going to stay constant at that starting function value. It's going to stay constant. When we get to the next interval, yes, the height will be different. But we only care about what's happening at the current value of x, which means that the radius increases and height stays constant. Okay, let's watch it. Let's see the picture here. So this is our image of what's happening here. I'll just start it here. Do you see how the radius increases? It's increasing, but the height is not at any current moment. At any current value of x, the radius is increasing, but the height is not. Okay? And so that's what defines our rate of change for this volume filling up. What is the rate of change, then, for the volume? So if it's the radius that's changing and not the height, so we worked on this last time. We finished up for our shell, how we get the rate of change? 2 pi RH. Is that what we had with the radius the rate of change when the radius was changing? Yep, 2 pi RH. Okay? So now the question is, what is our independent variable? What is our independent variable? We've got to write that rate of change function in terms of the independent variable. Right now it's not x. So that's just the rate kind of generically. We have to get that in terms of the independent variable, which is what in this situation? The independent variable is going to be either x or y. X. X is increasing, right? And I'm showing you x increasing right there. This is the current value of x right here. So we want in terms of x. That means we need to get the radius in terms of x, r. So we do 2 pi. We need to get what the radius is in terms of x and the height in terms of x. Okay? What is the radius in terms of x? So here's the question you can ask. Is it simply the x coordinate or simply the y coordinate? Or is it a big change in x or is it a big change in y? The radius. So here I'll pause it. So the radius is the radius of that shell that has the turquoise top. So right there, that's the radius. Is it the x coordinate, the y coordinate, some big change in x or some big change in y? You should just see it's the x coordinate. It's just the x coordinate. Will it always be the x coordinate? No, this thing could be turned on its head. This thing could be out away from the origin, so it could be something different. But in this case, our radius is just the x coordinate. What is the height of the shell? Simply the y coordinate, because it's from the x-axis up to the height. So that's simply the y coordinate. And what do we have for the y coordinate here? F of x, right? F of x. I didn't tell you. I don't think it tells you what the function is, right? F of x. Okay, so we're ready to write our accumulation of volume function then. Total accumulation of volume equals v sub 0 plus integral from 0 to x of rate of change times little change, right? Rate of change times little change in independent, but we have to use a new variable, right? So 2 pi t f of t dt. And what is f of 0 in this case? Or v of 0? 0. Because when x is 0, we don't have any accumulated volume yet. Okay, how do you represent the volume of the entirely filled? So the thing about this is now, if this is 0.8, we can use that function to say how much volume has been accumulated so far. How much volume has been accumulated so far right now, if we're at the current value of x is 0.8? Okay, you should be thinking v of 0.8. V of 0.8 would be the current amount of accumulated volume. Now, if the intervals are very, very small, right? So we're still kind of looking at the big interval situation, or the big delta x interval. But when we write this, what is that assuming? That those delta x intervals got very, very small. Okay? That's assuming those delta x intervals got very, very small. And so then the current accumulated volume when x reaches 0.8 is v of 0.8. What about the whole thing? I want to get the volume of the whole shell filled up. Again, v of 1, right? If that x value is 1, v of 1 now gives me the volume of this thing. That whole shell, v of 1. But the beauty of having the function is we can get the volume of the whole shell, or we can get any amount of volume along the way, right? Accumulation function lets us get the volume anywhere along the way, including the final volume of the whole thing, v of 1. Okay, try the bottom of the page. So the bottom of the page is the same setup, but the bottom of the page is now, you're going to start with delta y intervals, and we're going to fill the same shell with cylinders that are generated through delta y intervals. Yeah. And I'll start attendance. So take about 5 minutes. Yeah, you do. Is an angle measure. 360 is one plane. 360 is an angle measure. And if it's in the circumference, you would take the area of the circumference. Well, the circumference is different from every x value. So a small circumference here, it's bigger and bigger. 360 isn't a plane. 360 is an angle measure. Yeah. What's that? So, did you draw the intervals yet?
Not yet.
So just walk through the steps. If you walk through the steps, it might help you. So, yeah.
The rate function, is the x value in the rate function the initial value of x? Like
No, x is varying. X is our current value of x. It varies. Right? It's because the rate varies.
No, like the initial value inside of the particular interval.
So one thing, no,
Because
it's the outer radius. It's the one that's changing.
But you said the height remains the same.
Yep.
Inside the interval, right?
Yep.
So when we take f of x, that would be.
Yeah, it'd be f of x this is x at the start. This is the x of the, yeah, good question. Yeah, this is the x at the start. This is the x throughout the interval. But when things get small, they're the same, right? So this is for the one. Okay, I'm showing you what the current element looks like. Is that what you do? Something like that. Okay. In the current interval, so you should have drawn your y intervals, and now we're in the current interval. What's changing? The radius or height or both? Height only. In the current interval, radius stays the same. Okay? Height only. So therefore, our rate of change is? It's good. Is it pi r squared? Kind of, but that's not it. It's the area of the base, right? The area of the base, which is now it's a disk, but then with a hole in it. So remember what that rate was? Pi r outer squared minus pi r inner squared. And do we need to get this as our independent variable x or y? Is x increasing through delta x intervals, or is y increasing through delta y intervals? Y is increasing through delta y intervals. So we got to get that rate function in terms of y. So we're going to do r sub v of y. So we need to get the outer radius in terms of y and the inner radius in terms of y. What's the outer radius in terms of y? Of any one of those cylinders. It's so easy, it's hard, right? What's the outer radius? Always 1. Doesn't matter. It doesn't depend on y. It's just always 1. So we write 1.
I thought that was an x value.
What's that?
I thought that was an x value.
Yes, but it's the radius, right? So it is an x value because it's from here to here. But we need the radius, the outer radius of this thing, and that's distance 1. Who was asking that? Is it better? Does it make sense? Is it better?
Yeah, I was just, you said in terms of y, so I'm thinking like because it's an x value that we
Yeah, but it's because as a constant, there's no transferring to do. It's just 1, right? It's just 1. Yeah, it's a good question. Okay, so what about the inner radius? The inner radius is? So let's pause it here. So here we are on the current interval. And so the inner radius is from here to here. And again, we ask that question. Is that simply the x-coordinate? Is it simply the y-coordinate? Freudian slip. Is it simply the x-coordinate, simply the y-coordinate? A big change in x or a big change in y? Simply the x-coordinate, okay? So we could start by writing pi x squared, but so now we need let's define this function here. Let's say this function is I don't know, x cubed over 4. Suppose f of x was x cubed over 4, okay? And so we need to write this in terms of y. So yes, this is true. It's pi x squared because it's an x-coordinate, but that doesn't give us the rate function in terms of y. So how am I going to get the rate function in terms of y? I need to get that x value in terms of y. So I need to solve this for x, right? So if y equals x cubed over 4, that's going to say that I have to figure out what x is, and that'll give me x in terms of y. So I think it's the cube root of 4y, right? I'm going to multiply by 4. Solving for x, I get the cube root of 4y. So that's what goes here. So now we can write our volume function. Our volume now is in terms of x or y. Function of y. It's going to be the volume at 0 plus the integral from 0 to what? Y. And now we need our rate function, which is pi times 1 squared. I'll write it just for minus pi times. So it's x squared, but in terms of y. So I need this thing squared. The cube root of 4y These are t's. That's a t. Thank you. Yes, need a t. So now t stands for the value of y between 0 and the current value of y, right? So but then that thing's squared. Don't forget, we're not accumulating rates. We're accumulating small changes in volume. So we also need dt. Remember, this is rate times change in independent. Gives us a small change in dependent. It's like mdx, right? Whenever you write an integral, it's like back to day 1 or 2, mdx. We're accumulating little changes. Each little change is calculated by rate times change in independent. Questions on that volume function?
On the
Yes, please.
illustration, why is it that the previous one will disappear as it throws up?
Say it again.
For the accumulation over there, why does the previous one disappear?
Oh, because I just wanted, yes, that's the way I designed the animation, just to isolate the current interval. So I can, yeah, so great question. So I'm going to,
Still accumulating.
yes, like that, see? I'm glad you asked. So yes, we're still accumulating. I was just isolating the current interval. So this is what it looks like when it accumulates. Okay, and how would we get the total volume of the fully filled shell? How would we get the total volume of the fully filled shell? V of? So we know it's at x equals 1, which means that would be V of? If x is 1, y is 1/4. It'd be V of 1/4 is going to be my fully filled, it's the volume of the fully filled shell. V of 1/4. Or the integral from 0 to 1/4 of all that stuff, right? The integral from 0 to 1/4 of all that stuff. Questions on this example? Okay. Oh. Could I get... When we get to the end, you're going to pass up and down. Raise your hand if you didn't get one, okay? Raise your hand if you didn't get one. Is there an extra one over here?
Yeah, please.
Okay, for time's sake, I want to go right to part 2. Yeah. Let's go right to part 2. And you don't need to, so all the information you need is on that page that says example part 2. You're going to sketch. So here's the typical situation. You'll be given function and equations, and you have to come up with the region. So make sure you have the region right before you go on, or else you'll be doing lots of work that's just going in the wrong direction. So you want the region bounded by f of x equals x plus 2, g of x equals x squared, and x equals 0. So you need to sketch those without, so these are easy enough that you don't, no technology here to make the sketch. No technology. You got to figure out what region is that talking about. And once you have it, check, make sure it's correct. And then you can proceed with the questions. But check your region first. Check your region. If you don't have one, raise your hand. Okay, so look. This is what should relate to what you've been working on. Take a look. Let me make- What's that? It should be straight. Yeah, this is just my rendering. Just imagine it's straight. Yeah. This already existed, and I wanted to put functions on it that made it easier for you guys, so I made a straight line. So thank me later. Yes, that f of x should be straight.
Why does it not get the very end?
What's that?
That very last bit, it doesn't seem to ever.
Yeah, it's just the animation is it's not perfect. But yeah, it goes all the way to the corner. Yeah. Yeah. Okay, and then also we should did it have you draw the shell? I never showed you the shell. No, I have that. Where's that? Thought I did. Oh no, I don't have that. Is that it? No. Okay, so just quickly, the shell that you get, should it look like this? This is the shell that you get. So we'll draw it so you can see what's going on here. Just draw some more circles so you can actually picture it. All right, and the shell is what? It's like below that cone, right? It's like if this was like a rose, it's actually the the stuff of the rose, right? That's the shell that we're going to fill up where the rose would be. Okay, and so now we're going to fill it up through delta y intervals. And what do you notice happens here? So first of all, is there independent variable y or x? Y. So the independent variable is y, so we went at the rate of change with respect to y. So our rate, so then as y increases, do these cylinders, does the radius change or the height change or both? Height change. Okay? The height changes. And so the rate is going to be area of the base or 2 pi RH. Area of the base or area of the lateral surface? Area of the base, the blue, right? Area of the blue. But what do you notice about what's happening here? Look at the blue. Now watch. So what's different about this? What's going on here? Right. When we get to this point, is that y equals 2? When we get to 2, it changes. The function that's going to define the rate is going to change. Oh, now it's coming back down. So our rate function is going to be what we call a piecewise rate function. We have to define this rate function in pieces. We need one rate function for which interval? When y is from 0 to 2. We need one particular rate function. We'll say like this. And then we need another rate function when? From 2 to 4. So what will the general form of our rate function be in this lower region from 0 to 2? So what that rate will be? Here it comes, watch. Trust me, it's coming. There we go. So what will the rate function be down here? Just pi r squared. There's no hole. See, there's no hole. When y goes from 0 to 2, there's no hole in it. So the rate function will be just pi r squared. And we need to get... And then what will it be from 2 to 4? Right. It's going to be that difference of areas, right? The difference of disk areas. So we'll have pi r squared, and then we're going to have pi r outer squared minus pi r inner squared. Okay, so we want to get this done. It may take a couple extra minutes here. We want to get it done though. Okay, so and we need r in terms of x or y? Y is our independent variable, so we need that r in terms of y. So for this bottom one, what is the radius? There we go, there's a picture of it. What is the radius? Is it a x-coordinate, y-coordinate, a big change in x, or a big change in y? It's just the x-coordinate. But which x-coordinate is it? Yes, it's the x-coordinate for this one, right? And we need that in terms of y. So what is that? This function is that g. This is g and this is f. So we need the radius squared. And the radius is x, so we're really saying pi x squared, but we need that in terms of y. So it's going to be pi times. So you can say square root of y squared, right? But so g is the fact that y equals x squared. And so there it is. X squared's right there, so it's going to be pi y. Okay, next, so now later on, once we get past y equals 2, we've got this other situation where it's, could I ask you a favor? I'll give you back the time another day. Please don't pack up. We got to get this done. So we got the outer radius is what? It's the exact same one we had before. So this outer radius squared, we're just going to do pi y. Now what's the inner radius? So the f of x was x plus 2. So y equals x plus 2. So x equals y minus 2. And we need squared, right? Because it's radius squared. The radius is x for the f function. That radius is the same as y minus 2. And we need radius squared. So it's going to be y minus 2 squared. Okay, so this is our rate function in terms of y. Oops. It's piecewise. So when y is from 0 to 2, the rate is pi y. When the rate is from 2 to 4, it's pi y minus pi times y minus 2 quantity squared. So then the volume function needs to be defined piecewise also. But it's no problem because if we want the volume starting, the total volume starting at y equals 2, we know how to do that. What's the total volume starting at y equals 2? V of 2, which we'll get from the region from 0 to 2. So this will be piecewise. First piece is easy. Second piece will just be v of 2 plus integral from 2 to y of this rate function in terms of t. See that? So pi t minus pi times t minus 2 squared.
For the first one, would you put from 0 to
No, y is going to go from 0 to 2. So y is going to vary from 0 to 2.
So the interval would be from 0 to
No, the top one, we know it's variables. From. Sorry, did you say 0 to y? Yeah,
Yeah.
0 to y. I thought you meant this over here. Yep, 0 to y of what? Pi t dt. And then, because we have this total accumulation function formula that we know, we're starting at 2. So we're going to take all the volume we got when y equals 2 from up here, and then start accumulating at the new rate. From 2 to y, where y could go up to 4 now. Yes, the second range is from 2 to 4. Second range is from 2 to 4. Thanks for staying late. I'll give the time back another day. Get started on your homework. Don't wait.
I have a question.
Yeah, sure.
I heard you say that in this graph the height and the radius all change.
What's that?
You said in this graph the height and the radius all change.
Both change?
I think the height is not change. It's the
No, in each interval, the height of the cylinder increases, but the radius does not.
but
This is where the height is increasing, so I'll do the animation.
the height. I think the height is constant.
No, see, look. In each interval, the height is increasing. Do you guys want to meet today or not? For next week? You want to start meeting today at 1:15?
Today, that's what I was going to ask. Are we starting this week or next week?
Yeah, so I'm asking you. Do you want to?
Oh.
If we want to be ready for next week, we could do it today.
Okay.
Yeah.
I think this dt just mean the height. This one means the out radius minus.
Yeah, it's the area. So this is the area of the blue,
Yeah.
right? And that's what we said. When the height increases, the rate function will be the area of the base.
Yeah.
Remember we said that?
So
And if the radius increases, then the rate of change is the yellow. But that's not the radius isn't changing here. The height is changing, so the rate of change is the blue ring.
yes, but the dt represents the height.
Yes, the dt represents the height. That's right.
Yeah. Oh. But why
Because this is volume, right? This is the rate of change.
yeah. Why the height is also why the height is still change, but the I think the dt is constant every cylinder.
So dt represents this changing height.
Change height.
Yeah.
Okay.
So yeah. So y is increasing through these intervals, and that y is determining the height of the cylinder in the current interval. Yes, and you're right. That's the dt. And then the rate of change of the volume of this is the blue. It's the blue area.
Okay.
Is that better?
So in another graph, the independent value is x. That graph, the height and the radius is also all change.
Does anybody have a question? Before I'm going to get rid of this stuff that's up here. Does anyone have a question about this stuff?
Yeah.
I just wanted to dissect that a little bit, make sure I
So after we're talking about that with them, then we'll go back to the other one. You asked about the other one?
Yeah.
I don't want to take this off until their questions are answered. Is it okay?
Okay.
Yeah. Go ahead. So
do you guys have
I just have a quick question. Why do we have to define the piecewise function if we could just keep the area, like the difference of areas, and just define like the inner radius is 0 for the first part?
because it stays 0 from 0 to 2, and then suddenly at 2 it starts to change. So you can't.
So we couldn't keep the same rate and just define that like inner radius
Because
is
there's
0
no
from
there's
0 to 2.
no there's no function, there's no single function that's 0 from 0 to 2 and then x plus 2 from 2 to 4. Do you see? There's no single function that does that. It's got to be two different functions. You got to identify that it's 0 and then it's changing.
Okay.
So you can't make one function that does both of those things. But you're right. It's the same. It's the same idea, but you can't write just like one formula that gets that.
Okay.
You need to split it up into the two formulas.
Alright, that
Yeah.
makes sense.
Uh-huh.
Why do you have to put V2 on the bottom of the Piecewise function? Because if you're already 0 to 2 off,
Yeah. Because what is the function we're defining? V of y. It's the total accumulated volume from the bottom. So,
okay. But you're
like if I put in V of, I'm almost done, right? V like almost to the top. I want to get all the volume. So I'm going to get the first part and then all the accumulated volume since y equals 2.
yeah. So aren't you doing that twice if you put? Because like the accumulated volume from 0 to 2 is what's on the top, and that's good.
If you plugged in 2. If y was 2. That's V of 2.
I still don't understand something.
So it's a function too. Like the 0 to 2, we're going to have the function of volume accumulating down here. So from here to here, this is that function, accumulating volume, right? But when we're up here, we still want to know, what all the volume is, right? Starts at 2, right? It doesn't start at 0.
Oh, okay.
See?
Sorry. Yep. I understand.
Yeah.
Thank you.
Yep.
Okay, so it's basically the same as that one. It's just kind of going over what that is.
Yeah.
Essentially, the top one is just the accumulation up so you get 2.
Right.
And then
So
once you get 2, because there's the hole in the center, you have to get a new equation.
it's a new rate
So the
function.
bottom one is going to be the original accumulation, including 2.
No,
And the original,
up through
accumulation
2.
up to 2.
Up to 2.
And then it's going to be plus, and then your new accumulation after that.
That's right.
Which is going to be...
At the new rate.
Right.
At the new
And
rate.
That's the new rate. So then for the test, you're going to want us to write it, I'm assuming the test is all that, which is you'll want us to write it like that in the box, which is that essentially there'll be 2 equations.
If there's a piecewise rate function, if you want to do a total accumulation function of volume, you need a piecewise volume function.
Right, so that's how we need to write it in like...
Yeah.
Okay, I'm just double checking
Yeah.
that.
Yeah, I mean,
Interesting.
right.
Because it's not how I it makes sense when I'm looking at it. It's not what I originally thought of when I saw that. Okay, thank you so much.
Okay. Let's move up there. So we can give the desk to the next person. Do you have a question? She said we should meet at 1:15 today. Start today.
Yeah, that's fine. I don't
Okay. So we can talk about next week.
What should I do for recitation?
Oh, so you can go over get all their questions answered on this. You could do part 1, and then they can work on the homework that's due Wednesday.
Okay. Alright.
Is that good?
Yeah, that's fine. Yeah, because the GC file really helped out. That went by with the students for
Yeah. Yeah, and they were helped. Okay, great. Great.
So in the
Okay, thank you, Ben. Hold on.